Hello everyone, and welcome to Lecture 3. Today's objective will be frequency response irregularities, timbre, and finally filtration. One of the hardest questions you may have to answer this month is, what does something sound like? For instance, if I ask you what my voice sounds like, you know immediately what I sound like because you're listening to me talk. But if I were to ask you to describe my voice, the question becomes harder. This is because there is no right or wrong answer. Timbre, also known as sound quality, determined by frequency content and the sound envelope. Timbre is subjective, like the timbre of my voice is subjective. Right now I'm going to play you 3 different examples, each with different timbres. First, we'll start off with a few notes of a violin. Next, we'll listen to an example of a viola. Now, the viola and violin are very similar, but what makes the viola sound different from the violin is the size of the instrument. A violin is smaller than the viola. You may also find different instruments made of different materials, which will also affect timbre. For a final example, let's listen to a cello. With the same basic shape, but much larger, the timbre will be different. So with sound envelopes, you may remember these from previous classes. They're also known as ADSR. So we have the attack, and the decay, the sustain, and the release. So the first 2 categories are the ones that really determine timbre. That's the attack and decay. Don't get me wrong, all 4 are important, but we gain the most information from the sound, about the sound from the attack. There was this study done once where they took a group of subjects and they gave them 100 everyday sounds like dogs barking, cats meowing, doors closing, coughing, etc. And they were asked to identify each of these sounds, which is pretty easy. I'm sure all of them got all of them correct. Then what the people running the study did was they removed the initial attack from each of the sounds and then they reordered them. And what ended up happening is their ability to identify the sounds went out of the window completely. Another way to demonstrate the power of ADSR is to listen to reverse sounds. I can't remember what the first reverse sound I ever heard was, but I guarantee you that I wasn't able to identify what I was listening to. I just thought it was an effect of some kind. Maybe it was the reverse beat in Paul Revere, or the reverse solo, the bass solo in You Can Call Me Al is another example. Here is what just a regular reverse snare sounds like. So all of the frequencies that are present in both examples are exactly the same, but the sound envelope is completely different, and your ability to really determine what that sound is lost completely. The only way that you can tell is because you've heard what a reverse snare sounds like before. Now we're going to take a look at going from a complex wave to a simple waveform. If we add the right harmonics together, we can get a fundamental waveform like a square wave, which is an infinite number of odd order harmonics. If we take a low-pass filter and bring it down, we can make a very complex wave more simple. Theoretically, if we could remove them entirely, we would end up with a sine wave. There will be a resonant boost on the cutoff to accentuate each harmonic rate before it's removed. So take a listen. So harmonics are a second category that determine timbre. If we take a look at a violin versus a cello, for instance, we know that the violin has a higher frequency range than the cello, and that's due to the length of the strings. The shorter the length of the string, the higher the pitch, and the longer the length of the string, the lower the pitch. We could also think about a clarinet, which is made of wood, and that sounds very different than a saxophone that's made of brass. even though they both use a reed as a vibrating mechanism. We can tell the difference between the clarinet and saxophone due in part to the material that it's made out of. So a clarinet made out of wood sounds a little bit more mellow, whereas a saxophone made out of brass sounds a little more strident, also a little bit more harsh. So we have string length, we also have the material that the instrument is made out of, and these factors are a large factor in determining overtones, harmonics, and these things give the instrument its timbre. So in this next example, we'll start with a tone, and we'll start adding harmonics, going from the simple waveform to a complex waveform, again using a resonant boost on the cutting frequency of our low-pass filter. We can accentuate each harmonic as it's added. Let's take a look at the 4 different types of fundamental waveforms. We have a sine wave, a square wave, a triangle wave, and a sawtooth wave. The sine wave is a simple waveform with all energy concentrated at one frequency. There are no harmonics above the fundamental. The sine wave is also the fundamental frequency of all complex periodic waveforms. In this example, we're looking at an oscillogram at the top and a spectrogram at the bottom. It's playing a sine wave at 500 Hertz. What we can notice in the spectrogram is that only 500 Hertz is depicted by the blue bar. Since the sine wave is a pure tone, it has no harmonics. Therefore, we are only seeing the fundamental frequency represented by the spectrogram. Let's take a listen to the sine wave at 500 Hertz. A square wave is a non-sinusoidal waveform that contains an infinite number of odd-order harmonics. In this example, we're looking at a 500 Hz square wave through an oscillogram above and a spectrogram below. The fundamental frequency is 500 Hz. We can see it in our spectrogram, and we can also know that compared to the other blue bars being represented, it's the highest amplitude because it's the fundamental frequency. As we continue to the right of the fundamental frequency, we see the odd-ordered harmonic content of the square wave. Please note that as we're going up in frequency, the amplitude is actually decreasing. It's the harmonic content that gives each instrument its particular timbre, and there's no difference here in the square wave. It's the harmonic content that gives the square wave its timbre. That's why when you listen to people talk, you can actually differentiate between your mom and your sister. Both voices have different timbres. Now let's take a listen to the square wave at 500 Hz. A triangle wave is a non-sinusoidal waveform comprised of odd-order harmonics that decrease in amplitude very quickly as harmonic frequencies increase. Here's a 500 Hz triangle waveform shown above in the oscillogram and below in the spectrogram. Once again, the fundamental frequency of 500 Hz has the greatest amplitude. As we look to the right of the fundamental frequency, we can see the odd-ordered harmonics that comprise a triangle wave, and we can see that the amplitude decreases very rapidly, so that we can only really see one harmonic being represented. And it's because of that lack of harmonic content that the waveform is starting to look like a sine wave. And when we hear it, you'll notice that there's more in common from a triangle wave to a sine wave than there is from a triangle wave to a square wave. The sawtooth wave is a non-sinusoidal waveform as well that contains both even and odd-ordered harmonics. In this example, we're seeing a 500 Hz sawtooth waveform in the oscillogram above and the spectrogram below. Again, 500 Hz is the fundamental frequency and has the highest amplitude of all frequencies being represented. Frequencies that are contained in the odd and even harmonics are represented to the right of the fundamental, and they vary in degrees of amplitude. Let's listen to the sawtooth wave at 500 Hz. So when we're talking about odd order harmonics and even order harmonics and the comparison between the two, generally odd order harmonics are harsh and even order harmonics are smooth. We can actually demonstrate this by using, I guess you could call it mouth filtration. So when we make the sound this is a pretty solid representation of the full harmonic contents of our voice. We can change the shape of our throat, change the shape of our mouth and position of our tongue to filter out frequencies so that we can get just the even order harmonics. And when we do that, we are left with the oo sound. So we go ooh, and that sounds pretty smooth. Now we can also change our shape of our throat and mouth to filter out the even order harmonics, and we can end up with the sound E, which is generally very harsh sounding because of the odd order harmonics represented. So let's take a listen. E. You can try that out on your own. Alright, let's move on to equalizers. Equalizers are a system of filters designed to alter the frequency response characteristics of an audio signal. Now, most of the time in an audio production, when we're using EQs, we're using them to isolate and remove problem frequencies. Other times, we can actually use an EQ to boost the presence of a signal. And finally, we can use EQs to create a type of effect. One of the most common of these is to create the effect of a person speaking through a telephone. Generally, there are three parameters to the EQ. We have our frequency selector, and then we have the gain. So you can choose the frequency, and then you can turn that frequency up or down. And then we have this awesome thing called the Q, which is a bandwidth selector. So we can choose the frequency, we can choose to boost it or cut it, and then we can choose how many frequencies on either side of that center frequency are affected. When we have a wide Q, we have a lot of frequencies on either side of the frequency, or we could notch it out and make it very narrow. So we're going to look at the tom drum first. We'll listen to it unaltered, and then we'll listen to it EQ'd so that the harmonics are isolated and actually boosted by narrow bands of EQ. Then we'll turn that off so we can hear the tom drum unaltered once again. And then we'll listen to that same tom drum with the isolated harmonics removed. With the harmonics boosted, it's amazing how melodic the tom drum became all of a sudden. So let's repeat this exercise with a different instrument, the gong. When we get to the part where we boost the isolated harmonics of the gong, I want you to pay particular attention to the really interesting echo harmonic that's happening around 1.5K. So here is an example of something called auditory scene analysis. Our ears have the ability to hone in on specific frequencies in a crowded sound field, similar to being able to focus in on a single instrument when listening to a whole band play, or trying to listen to your friend talk in a crowded room. These next examples take single frequencies out of white noise, and then we add it back. Your ears should be able to focus on that one frequency when you add it back, even with all of the others playing. It's a little hard to do with 500 Hz, but it definitely gets easier with 1K, 2K, and finally 5K. So let's do this with 500 Hz first. Now let's listen to 1000 Hertz. 2000 Hertz. And finally 5000. Now, when you're doing these on the quiz, what I suggest, if you're having trouble identifying the frequency or even hearing that frequency, I would do all of these questions in a group before answering any of the questions. And this is a good rule of thumb for most of our quizzes. This way you'll be able to hear each individual audio example in a row, and you can kind of use the power of deduction to kind of sort through your answers. So the last thing I want to show you is using an EQ as a telephone effect. So let's take a look at an EQ for the telephone effect for a female voice, and you'll notice that everything below 1K is cut and everything above 2K is cut. So this will be a female voice first.
It has become appallingly obvious that our technology has exceeded our humanity. It has become appallingly obvious that our technology has exceeded our humanity.
Let's repeat the same exercise, but with a male voice.
Only two things are infinite, the universe and human stupidity, and I'm not sure about the former. Only two things are infinite, the universe and human stupidity, and I'm not sure about the former.
And for this final example of EQ, I'm going to show you how you can use EQ to enhance the presence of a voice. So in this instance, we're actually cutting some of the low frequencies and boosting some of the mid-highs and highs to give this vocal more presence.
Only two things are infinite, the universe and human stupidity, and I'm not sure about the former. Only two things are infinite, the universe and human stupidity, and I'm not sure about the former.
And that's the end of the lecture. Thank you guys so much for watching, and good luck on your quizzes. Please contact me if you have any questions whatsoever. Take care.